which is on the geometry of the symmetrized bidisc. So, sir, you may please take over.
Thank you, Haripodo. And I'm very grateful to the organizers for inviting me to give this talk, and I'm grateful and honored. And yeah, it's always a pleasure to talk on one's own work. I'm slightly apologetic because this is an operator theory seminar, and this time for a change, I have no operators. That sounds strange, but that is how it is. Okay, so this is on the geometry of a certain set, a certain domain in C2, which I have been interested in for maybe about 10 years now. And it's on the geometry. So far, we have done function analysis and operator theory there, but this time the talk is, the work is on the geometry. Okay, joint work with Anindya Bishwas on the left and Annoy Moitra on the right. Anindya is my current PhD student, and Annoy finished his PhD with Gautam Bharali in our department, and this work was done just after his PhD, or at the time of when he was about to submit his PhD. It's on the archive. It's on the archive, and just a few days ago we heard that it's due to appear at Indiana University Math Journal. All right. So now we dive in. The set that we are going to consider is this. The name is self-explanatory. It's the symmetrized bidisc, because you take the bidisc and then symmetrize it, apply the two elementary symmetric functions on it, and you get this. Now, in this form, the set was introduced by Agler and Young at the end of 1990s. It has attracted a great deal of attention, both in the operator theory and the complex geometry communities. So it's one of the very few domains where you can actually construct a minimal boundary normal dilation for a pair of commuting boundary operators for which this is the spectral set. Now, this is a success. It cannot always be done. It can rarely be done, and it can be done in this case. So it's a nice set. It lends itself amenable to operator theory. And consequently, there is an interpolation theory as well in the a la Saracen, in the Saracen style. You can pursue that here, gives a very nice realization formula and corresponding interpolation. On the complex geometry side, this has been greatly worked upon by the complex geometers. Perhaps one of the early breakthroughs was a very striking fact is that the Tirthankar and Kobayashi pseudo-distances agree the non-convex domain. So Lempert's theorem doesn't apply, but you can still show that the Tirthankar and Kobayashi pseudo-distances agree. Just to give you the background of why this has been at the center of attention of many people in analysis. I think the most lovable part of the work that I enjoyed doing it is we figured out slowly that a biholomorphic copy of G was introduced by Elie Cartan in 1933. Now that's a surprise when you come across such a thing. Well, we'll have new characterizations of G, but those are corollaries. The real pleasure was discovering this connection with a domain already known to complex analysts for a great many years. Okay, now how did you come to do this? This work was really motivated by an article of Agler, Likova, and Young, which appeared in 2019. I'll take a couple of minutes to describe Agler, Likova, Young's work. So what they did is, well, Agler and Young are operator theorists as well, but after working on this domain, as far as the operator theory is concerned, they thought that let's study its geometry for a while. Now, they gave a foliation. Now, there is a very natural analytic disk that you can consider inside G, namely the set consisting of all pairs of the form 2z comma z square. I haven't written it here, but this is what this R is. A complex geodesic is a fancy name for the range of an analytic map, which also has an analytic left inverse. Now, so consider this special complex geodesic 2z comma z square. So all you are doing is mapping the disk there. So the disk first goes to maybe the bidisc as the pair zz, and then you symmetrize it and it goes to 2z comma z square. Okay, fine. So consider this analytic disk, call that, so they called it the royal variety. So the notation R, and using that as the base, consider other complex geodesics that meet R at only one point and have non-trivial stabilizers. That is, there are elements in the automorphism group of G other than identity which stabilize the complex geodesic. Now they showed that this collection foliate G. So these complex geodesics foliate G, which was nice. I mean, they got a copy of the unit disk in there, and at every point of that copy of the unit disk inside G, they constructed a fiber. This disk along with the fiber foliates G. That's nice. And then they studied the properties. They came up with two properties which they defined. They called it synchrony and sharpness. And roughly speaking, the characterization theorem said that if you had a domain in which you have such a special complex geodesic like the royal variety, and you have fibers, and if they also satisfy synchrony and sharpness, then it has to be biholomorphic with. So I'm only describing it roughly. So this paper we were reading, and we figured out that perhaps something somewhat different could be done. Okay, so what is it that we did differently? What we did is the following. Okay, give a name for the symmetrization map. I call it SYM. So first note the automorphism group of the domain. Corresponding to every automorphism of the disk, we can set an automorphism of the symmetrized bidisc by as follows. So any element is of the form Z1 plus Z2 comma Z1 Z2, Z1 and Z2 coming from the unit disk. So then why not apply the unit disk automorphism phi on Z1 and Z2 and symmetrize them? That's fine. That gives an automorphism, and turns out that these are all. So the automorphism group is the same as the automorphism group of D. So that's an elementary fact. Fine. So all that I and Ananda were trying at the beginning is this automorphism group clearly doesn't act transitively, unlike the disk. So find out the orbits. So you are just interested in finding out the orbits. So apply the automorphism group and find out its orbits. Turns out, So turns out that if you do that, then you get a fibration of G over an interval of the real line. And in this case, our leaves, the fibers, which are the orbits are three-dimensional hypersurfaces. Almost always, except one. So there is only one exception. All the fibers are three-dimensional hypersurfaces. We are in C2, except one fiber, which is the disk in the form of the royal variety. So that root is as follows. So ORG does not act transitively. You can this you can see very easily. For example, A0 and B0 are in the symmetrized bidisc, but if you choose A and B between 0 and 1, and clearly there is no automorphism, we'll take this to that. So partitions. Okay. Okay. So what we do is look at the last bit of the slide first. So you take a point SP and write it as Z1 plus Z2 comma Z1 Z2, and simply consider A equal to modulus Z1 minus Z2 by 1 minus Z1 bar Z2. It doesn't matter whether you interchange Z1 and Z2. So the symmetrization map is of course a 2-to-1 map. You can interchange Z1 and Z2. Interchanging that does not change A. So go to this A. This A is between 0 and 1, close 0, open 1. So consider this say a half open interval in the real line, and then this is the base, and the fibers are for every A in 0, 1, you take the orbit. So apply all automorphisms to the point. So here is a matter of notation here. This first bracket A comma 0 is the point in the symmetrized bidisc, and the square bracket is the equivalence class. So the equivalence classes are the 3-dimensional hypersurfaces that I mentioned earlier. So the foliation is you have the interval close 0, open 1, and for every point A in there, you have applied all the automorphisms, and you get something, and that's it. Okay. Some trivia. If you take 2 points, SP and TQ, in the fiber 0, where A is not 0, A is strictly between 0 and 1, then there are exactly 2 automorphisms interchanging SP and TQ. That's easy to see. However, when A is 0, so the point 0, 0 is in the symmetrized bidisc, and look at the fiber over 0, 0. This is precisely the Royal variety, and then for any 2 points in the Royal variety, there are infinitely many automorphisms interchanging them. So the Royal variety is the fiber at the point 0, 0. So corresponding to A equal to 0, that's the Royal variety. And when A is between 0 and 1, the orbits are 3-dimensional hypersurfaces. So we figured out this much. That was very nice. Now, although the Royal variety has been denoted by R before in the literature, we needed to be consistent. So we called L suffix A as the fiber over the point A0. Then the Royal variety is L0. Okay, so these are the definitions. LA is just H phi. H phi is a typical automorphism element of G applied to the point A0 of the symmetrized bidisc. So we have these collections. LA 0 less than equal to A less than 1, and we have the interval close 0, open 1. That's all, and that constitutes the symmetrized bidisc. Okay, it's good to keep touch with the bidisc. A lot of things sometimes can be actually obtained from there by symmetrizing. So this is the automorphism group, which is a subgroup of the automorphism group of D2. That's of our interest, because if you notice, H phi was just the symmetrization of this. So consider this subgroup ORT D of ORT D2. Obviously, it doesn't act transitively. So then you can consider the orbits here as well. So consider the orbits here, and symmetrization of these orbits turn out to be our orbits in the symmetrized bidisc. Fine. And this is the function that I showed you earlier. In the bidisc coordinate, it's this. And in the internal symmetrized bidisc coordinates, it's this, the expression on the right side. Okay, so at the end of it, whether we are on the bidisc or on the symmetrized bidisc, the map that we consider is just this, modulus Z1 minus Z2 by 1 minus Z1 by Z2, and we come to a half open interval of the real line on which our fibers stand. Okay, this is it's a submersion from, if you leave out the Royal variety, that's always an exception. So for a lot of times you may need to leave it out. Otherwise it's a submersion, and obviously there is a Z2 action. So if you quotient FA by Z2, then we get this theorem. Okay. So here is a name for this map, which I said this modulus Z1 minus Z2 by 1 minus Z1 bar Z2. This notation phi suffix Z1 stands for, so phi suffix A acting on Z is Z minus A by 1 minus A bar Z, the automorphism. And so consider this map, then whatever I said so far is summarized in this theorem. It is a submersion, and because it's a submersion, it straightforward follows that it defines a 3-dimensional foliation. The leaves are this, each leaf is a real three-dimensional hypersurface. So although we are in C2, but the leaves are real three-dimensional hypersurface. And there is a quotienting of the bidisc leaves to the symmetrized bidisc. A final analysis shows the following, that all these three-dimensional hypersurfaces that we have been talking about so far, so leave the Royal variety again, that's an analytic disk, it's a one complex dimensional thing. All the others are diffeomorphic to each other. They're three-dimensional real hypersurfaces, so it makes sense to ask whether they're diffeomorphic or not. And we end up showing that these are all diffeomorphic to each other. Okay. Yeah, I mean, it's also diffeomorphic to OT D quotiented with Z2, but that's not the prime thing of importance here. It's just that the leaves are diffeomorphic to each other. Okay, now things start getting more interesting because, well, they are three real dimensionals and they are diffeomorphic. But there is an ambient complex space. They're sitting in C2. So I won't be able to go into the details of this concept, the so-called CR geometry, and the excellent exposition from which we learned a bit of it is John P. D'Angelo, his chapter 3 or so. And he says it's not clear whether CR is for Cauchy-Riemann or for complex real. Apparently, people think that it could be for Cauchy-Riemann, could be for complex real. Okay, whatever it is, but the concept is extremely interesting. Suppose you have a real submanifold in Cn. So the tangent spaces, obviously, I mean, you could consider it just a real submanifold. So the tangent spaces are real vector spaces. But there is an ambient complex structure. And it will be a shame if the complex structure is wasted, right? You should be able to complexify the tangent spaces. So the resulting thing becomes a complex vector space using the ambient complex structure. Now, the moment you have done it, you should ask between complex linear maps between them. So if you have a map F from M1 to M2, keep in mind that the leaves are diffeomorphic. So we have a diffeomorphism, suppose, from between two leaves. And the question is, from one complexified tangent space to the other complexified tangent space, whether the differential map is a complex linear map or not. So such a thing is called a CR map. Two CR manifolds are said to be CR equivalent if there is a diffeomorphism that is also a CR map. So we have shown that the leaves are diffeomorphic. But in the presence of the complex structure, now it makes sense to ask whether they are CR equivalent or not. This we did not know. At this point, it was getting clear to us that we need a hardcore complex analyst. So Anindo roped in Onnoy, and this was such a win-win collaboration. So although we didn't know this, but you can talk of something else. So it was getting clear to us that we have to study the leaves. At this point, we suspected that this domain must have been present in complex analysis literature in some form, but how to find it? So we need more information about the leaves. So one such is the Levi pseudoconvexity. What is this? So suppose you have a domain with a somewhat nice boundary, and take a boundary point, take a defining function for omega. So suppose rho is such a function which is less than 0 gives omega, greater than 0 gives outside omega, and equal to 0 gives the boundary. We say that the boundary is Levi pseudoconvex at P if in this case just a 2 cross 2 matrix, because n is equal to 2. So you take these derivatives, it becomes like a Hessian. It's a 2 cross 2 matrix, and we want that to be positive semi-definite. That's all it means. The vectors W's are coming from the tangent space. So it was particularly simple because we only have to compute a 2 cross 2 matrix. Of course, that runs into computational issues, but that's a different thing. So this expression here is called the Levi form. Now, you call it strongly pseudoconvex, strongly Levi pseudoconvex, if the inequality is strictly greater rather than greater than equal to. And if it happens for all boundary points, then you say that the domain or the boundary, whichever, I mean, sometimes you say the domain is Levi pseudoconvex, sometimes you say the boundary is Levi pseudoconvex, but the meaning is clear. All points satisfy this, all points P satisfy this. So this is one more thing that we could investigate. And we get hold of, well, again, the bidisc comes of help. We get hold of a function which plays the role of the row in the last slide, and we compute this. And of course, as I said, the computation runs into some amount of difficulty, but then one is able to manage it. And we are able to show that they're all strongly pseudoconvex in the sense of Levi. All the three-dimensional orbits. So all these hypersurfaces. So what happens is this defining function actually defines a part of the symmetrized bidisc, of which this orbit is the boundary. So we can apply this concept. So they are all strongly pseudoconvex. Fine. So with these things in hand, we started searching, and we found that Isaev had made it his life's motto, I think, in what he calls, let's say, MN manifolds. Now, there is an ambiguity here. The first M stands for a complex dimension. The second N stands for real dimension. So in this case, we needed to look at his 2008 paper, which studied all the 2-3 manifolds. So 2-3 means 2 is complex dimension 2, and 3 is the dimensions of the orbits under the actions of the automorphism group, but real dimension. And he had a whole list of them, out of which we found out one, matching the properties, basically matching the properties. Okay. And then I think we came to know from Isaev that this had been first studied by Carton in 1933. Okay. Automorphism group is the special orthogonal 2-1 with the identity component. So the connected component of SO21, which contains identity. SO21 is the special means determinant 1, O for orthogonal, and 3 cross 3 real matrices. And this 2-1 stands for, it preserves a certain form. The form is 1, 1, minus 1. So 2 positive and 1 negative, indefinite form. It preserves this indefinite form. And SO21 0, of course, you immediately see that it's really SL2R in disguise, so that it's the automorphism group of D. Now that encourages us more. This is the action. This is, so SO21, it's a 3 cross 3 orthogonal matrix, and it acts like this. You take a pair Z1, Z2, and this is just the action. Okay. Now, what does the automorphism group of this strange domain D1 do to D1? You apply the automorphism group and look at its orbits. Again, turns out that it has a special orbit, which I think this is Isaev's notation. He calls it eta 0. Eta 0 is special. It's really just a complex curve. And the rest, eta c, for c between 0 and 1, are again 3 real dimensional hypersurfaces. Okay, D1 is contained in a certain bigger domain, and I have written it only because it comes handy in our computations. We shall need this. Okay, very nice. So then, I mean, finally, from Isaev's long list, one was able to kind of zero down on this D1. And then it was clear that it was a matter of just writing down the biholomorphism. So this is the intuition, how we wrote down. I mean, remember that the domain looks pretty complicated. The domain is this. Maybe it doesn't look so complicated to the complex analyst, but it's slightly frightening to function analysts. Okay, so how do we write down? And here is the motivation. we really look at the fibers. And what helps us is imagining Z1 is positive. So this eta 0 is really a complex curve, but in some sense, and I'm speaking somewhat intuitively here, it's not really just like the disk, it's more like the upper half plane. So from the upper half plane, you come to the disk. This is where I'm hovering the cursor, is like the Riemann mapping theorem. And once you are able to write Z1 like that, Z2 gets fixed automatically because of this relation, 1 plus Z1 square minus Z2 square equal to 0. Okay, so this gives us a map which allows us to identify eta 0 as the disk. That is, see, after all, we have to identify the Royal variety with eta 0, and this is a map which does that. Once we do that, the biholomorphism is just written down. It's not very difficult to write down the biholomorphism. Motivated by looking at the leaves again, and specifically at the leaf at the point 0, we knew what to do, what to write down what should be the biholomorphism. So this is really the biholomorphism. So this is an unbounded realization of the symmetrized bidisc. Symmetrized bidisc is a nice bounded domain, but this is an unbounded thing. D1 is an unbounded thing, and so we write that. It gives us as a minor corollary. It gives us some new characterizations of G. G has a number of characterizations known, of course, but this gives us new characterizations of G, because now we can leverage this. We can use known facts about D1. Okay, it gives a characterization of G. Start with the 2-3 manifold, 2-3 in the language of Isaev again. Remember, complex 2-dimensional with actions of automorphism group acting in such a way that leaves are 3-dimensional. Let GM be that connected component of the automorphism group which contains the identity. Suppose that all orbits of M under GM except only one are strongly pseudoconvex, 3-dimensional real hypersurfaces, and that the sole remaining orbit is a complex curve. And then a kind of technical condition. Suppose there is an epsilon positive such that for every C in 1 minus epsilon comma 1, there is the 3-dimensional orbit O such that O is CR equivalent to eta C. Then M is biholomorphic to G. So this is a characterization of the symmetrized bidisc. But rather than the characterization, there is an interesting corollary of the biholomorphism, namely the orbits of G are diffeomorphic but not CR equivalent, because Isaev showed that orbits of D1 are not CR equivalent, and this is something we wouldn't have been able to figure out otherwise by looking at just the symmetrized bidisc. They're not CR equivalent. Okay, so that's the first part. We go into some, for the rest, we go into some nice applications. Since Isaev had a long list, he also mentioned 2 other spaces, which he denoted by, well, these are his notations. I'm not writing down those spaces here. He reasoned abstractly that these are biholomorphic to the bidisc, both of them. Now that we have been able to construct a biholomorphism once, we can do it more. And we wrote down the explicit biholomorphisms between the bidisc and these 2, omega 1 and D1, 2. Okay, I'll show one of them explicitly and we'll see whether we have the time for the other one. Okay, omega 1 is this. So all UV in C2 such that this happens. And after a little bit of jugglery, you can transform these things to, so set U square plus V square minus 1 equal to U1 square and V equal to V1. Then the inequality that is there in the definition can be written slightly differently. It becomes mod 1 plus U1 square minus V1 square less than 1 plus mod u1 square minus mod v1 square. Why we wanted it in this form is, see, we had worked hard on D1. So if we can get back to D1 somehow, it helps us. This is similar to the definition of D1. So using our already known knowledge, using the expression of F is the biholomorphism between G and D1. We write U1 as this and V1 as this, and hence, and then we can go back to U and V again, and we get U square is this, and V. So Z and W come from disk, because we're after all trying to get a biholomorphism with bidisc. So here is the biholomorphism with the bidisc. The last line is the biholomorphism with the bidisc. Okay, here it's written explicitly. So nice looking biholomorphism between, I don't know why Isai actually did not write it down. Perhaps he reasoned that there is a biholomorphism, but he didn't actually write it down. Now there is a natural question. We have the symmetrization map from the bidisc to the symmetrized bidisc, and we have this biholomorphism between D2 and omega 1. And of course, we have the biholomorphism between G, the symmetrized bidisc, and D1. So you should be able to quote unquote symmetrize omega 1 to get D1. And that again can be written down. So we have written down the biholomorphism between D2 and omega 1. We have written down the biholomorphism between G and D1. We have written, we know the symmetrization map from D2 to G. So it was a question of chasing the diagram, that is, go back from D1 to G and then go to the two-fold cover D2 and then apply H. And doing all this, you can find out a map here, which is this. So take uv in omega 1 and send it to v remains v, and u goes to I root 1 minus u square minus v square, and so omega 1 goes to d1. This is exactly like the symmetrization map from d2 to g, this time from omega 1 to d1. It requires some work to show that it's holomorphic, but that's the technical part which can be done. So that's what is written at the end of at the bottom of the slide, that this 1 minus u square minus v square, where uv belongs to omega 1, is contained in the slit plane, c minus the negative real line, and hence things are well defined. There's no problem in taking a square root. Okay, that was rather pleasing, because I don't know whether Isai imagined that you can go from omega 1 to d1 in this way. This of course comes from the knowledge that you go from d2 to g. So hence you must be able to go from omega 1 to d1. Yeah. Now comes another interesting thing. Isai gave an exhaustion of D1. Here, the parameter C has changed its role. I'll explain that. Remember when we defined D1, the foliation was again on 0, 1, close 0, open 1. For this particular thing that I'm going to describe now, so there C belonged to C, 0 less than equal to C less than 1. It helps if we take 1 by C instead of C for this particular thing, which is an exhaustion. So when you take 1 by C, it becomes 1 less than C, our new C, which is old 1 by C, 1 less than C less than equal to infinity. Infinity is now included, 1 is excluded. And then consider these, D suffix C. It is like D1, except that you are cutting at the point C. That's all you are doing really. So now the fibration is not over the base 0, 1, it's over the base 1 infinity. And you are not going all the way to infinity. You are kind of cutting it at C and looking at only that part. And as you increase C, it's filling up whole D1. That's what is happening. So this is the exhaustion. The Isai's domain D1 is is this. This is taken directly from his side. But now we cannot resist to apply the biholomorphism, of course. So pull it back, pull back everything to G1, to G, to the symmetrized bidisc. And so this capital F is the biholomorphism. So F inverse DC, call that GC, it must give us something inside the symmetrized bidisc. And since it exhausts D1, finally the union has to exhaust G as well. And expression for GC. Okay. So this is the expression for GC. Just applying the biholomorphism. You just apply the biholomorphism, pull back DC, and this is what we get in the end. So this GC, people who work with symmetrized bidisc will notice that this actually corresponds with a certain known characterization of the symmetrized bidisc. We have just put in the C here. Otherwise, it's a known characterization. This characterization here, it's so if you cut down at C, this is what you get. So this gives an exhaustion of G, and all of these GCs, all these domains GC have the same automorphism group. The automorphism groups are the same as the automorphism group of G, which is the automorphism group of D. Okay. Using.
Excuse me, may I have a question?
Yeah.
Do you know anything about the geometry of this domains GC? I mean, something related to convexity or some kind of convexity?
I don't know. We haven't studied convexity of this. No.
So it cannot be convex because the exhaustion gives non-convex domains. Nevertheless, there are some other notions related with the convexity. Okay. So thanks for the answer.
Yeah, I understand what you're saying. It cannot be convex, of course, but yes, I don't know whether you mean C-convex, right? Whether they can.
So yeah, either C convexity or some other notions related to convexity, to complex convexity. But okay.
Yeah, we don't know. We haven't thought about this.
Yeah. Okay.
Yeah, obviously it cannot be convex, but more than that we cannot say. We should think about. We'll try to find out. Yeah, right. Using known characterizations of the symmetrized bidisc, one can find new characterizations of D1, a whole bunch of them. Again, people who have seen characterizations of symmetrized bidisc before would notice that all that we are doing is taking every characterization of the symmetrized bidisc, applying the biholomorphic map, and taking it to D1. Most of it. There is something interesting here. Namely, note that you could ask the following question. Go back to Agler, Likova, Young's work. They had the royal variety, which is really the unique disk in disguise, and on it they had the complex geodesics, which are which are the fibers, and they fibrated the symmetrized bidisc. Now that we have a biholomorphism between the symmetrized bidisc and D1, so D1 also should have such a structure like what they did. So apply the biholomorphism to the royal variety. It will bring you to what I called eta 0, and then apply the biholomorphism to the other geodesics, which were the fibers, to see where they come. So a result similar to theirs should be available here as well. And that's really what this characterization 9 is. It's not explicitly stated here, but this exactly does just that. You can explicitly write down the Agler-Likova-Young picture for D1 as well. It's a matter of applying the biholomorphism carefully. Okay. Yeah, okay. The last thing is the is what I mentioned, this D12, which Isaev did, and Isaev said that it's biholomorphic to D2. He didn't give an explicit biholomorphism, and this also we can write down. I mean, I won't go into the details right here because it's very difficult to explain. You go through CP3. You go through CP3, and then you can actually write down the biholomorphism. Okay, so the entire thing is written here, and well, this really gives the biholomorphism from D2 to D12. This is also there in our work, and correspondingly you can ask the symmetrization map here as well. What should be the symmetrization map from D12 to D1? That also you can that also one can write down. Okay, I think that's it. I'm early, but maybe that's good. It's so this is a okay, some things. Number one, Cartan was really interested in the three-dimensional hypersurfaces. There is less mention of the domains in Cartan's paper. Of course, it's a very long paper and it's in French. So we read whatever we could, bits and pieces of it, not the whole thing for sure. Isaev's 2008 paper is very, very informative. So he classifies all two-dimensional manifolds with three-dimensional automorphism group, and Agler-Likova-Young is what motivated us in starting this project in the first place. This paper is to appear in Indian University Math Journal. It's available on the archive, and I'm slightly proud that this is the first paper that I have written which doesn't have the mathematics subject classification 46 or 47. Thank you.
Any question, comments you can ask?
Yeah, I have a question. And so, hello everybody, my name is Gautam. I had a question and a comment. So looking at your references, and in particular, I remember multiple conversations with Onindo in trying to access this work by Cartan. It's kind of inaccessible. And of course, Isaev gives you a snapshot of the key results of this work by Cartan, which is, I think, a partial list of the CR equivalence classes of these real three manifolds, right?
Right.
And since CR diffeomorphisms are much more rigid than diffeomorphisms,
yes,
this is sort of gigantic. And I'm still in hindsight, after having heard of your results, I'm in hindsight thinking about the role of Cartan's work. Do I understand correctly that at some point of time, the question that had arisen in your mind was, are these real three-dimensional fibers, which are strictly pseudoconvex surfaces? Were you toying with the idea of whether these were initially, whether these were actually even CR diffeomorphic? And then later on, you realized that they are all CR inequivalent.
Well, Gautam, to tell you the truth, I didn't know about the notion of CR equivalence. Well, my complex analysis was not that strong, never that strong. And I figured it out while doing this work. I figured out this notion, and then I read bits of D'Angelo, John P. D'Angelo. And so when we were kind of groping with this, this question, of course, did arise, but or more or less right at that time, we found that we figured out that Isayev's D1 fits into our scheme, and there it's not, the leaves are not CR equivalent. So then immediately we saw that the leaves here in the symmetrized bidisc are not CR equivalent. It's not that we had spent a great deal of time trying to prove or disprove it.
I see. Yeah. And a quick comment. I deliberately did not interrupt you when you were speaking because this novel symmetrization that you had, it's pretty distinctive. So I think everyone will remember. One of the coordinates is I times an analytic square root of 1 minus u squared minus v squared. So you made a comment, and so I want to make a comment on the comment, which is that you said that key to determining this novel symmetrization was knowing from Isayev beforehand that the bidisc and omega-1 are biholomorphic. So I just wanted to make a comment that, in fact, the strategy that you used in order to compute an unknown holomorphic map, one sees this quite often in several complex variables of a certain style. And one notable example is there are these classes of bounded domains called egg domains. And they happen to have, one knows abstractly that they have several nice unbounded realizations. And the question arises is that what is the explicit biholomorphism from the egg domain to a nice unbounded realization? And the strategy is exactly what you used, which is these egg domains admit, slightly different from your situation, they admit a proper holomorphic map from the unit Euclidean ball onto them. And one knows that the Cayley map is a biholomorphism from the unit Euclidean ball onto the Siegel upper half space. And so one sort of chases the diagram. So the interesting thing here is, in your case, what was unknown was a certain proper map, the symmetrization. In this problem, the thing that needs to be determined is this realization map. And the data that we happen to have, that we happen to know because it's obvious in that kind of geometry, are the proper maps. So I thought I'd just make this comment because trying to model a certain arrow in terms of another arrow in a square of a commutative diagram, that comes up quite often.
Thank you, Gautam. And I think we have a copy of Caton's paper, which I can share with you.
Ah, great. Yeah.
Any more questions, comments?
Yes. Very nice talk, Tirthankar. I have, you've, as you mentioned, you were avoiding talking about operator theory, but of course, the natural question that comes up for these domains then is for, let's say D1 and D that, since you know that for the symmetrized bidisc, you have rational annihilation holding, is there a similar result for these sorts of domains as well?
Yeah, Michael, we haven't thought about it. I have been a little too overwhelmed by all these complex analytic concepts. So we haven't had time to, but yeah, sure. Yes, maybe. Yes. Especially, I think one of the interesting things will be in connection to operator theory is the curious thing that numerical radius makes a presence for the dilation, the rational dilation for the symmetrized bidisc. Now, as you know, there is this, it has appeared in your work as well, all these row dilations, unitary row dilations. And I have a strong suspicion that they're connected, but the domains are perhaps waiting to be discovered, and maybe these could give you new domains where those unitary row dilations, I mean, not instead of the, I mean, the numerical radius is just one of those rows. So perhaps they should make their presence felt in relation to one of these domains.
Okay, and another question, if you start instead of with the bidisc, if you started with, say, like the annulus, are there similar, can you come up with similar results in this context?
Can you come again? I didn't quite understand.
So I don't know if it makes sense or not, but if you were instead of working with the bidisc, if you worked with the annulus, I don't know if there's some natural way of talking about similar types of results in this context, because again, you have again, I'm thinking ahead to rational dilation results. It's one of the few other domains where you know that rational dilation holds, and well.
So Michael, when you say the annulus, do you mean the twofold symmetric product of an annulus with itself? Or, I mean, presumably not just the complex one-dimensional annulus, right?
Well, no, in fact, actually, I think it would have to be with the complex one-dimensional annulus, because in fact, I seriously doubt whether there is a rational dilation result for the product. So I don't know. I mean, again, maybe it does. Maybe the question doesn't make sense in this.
So for the twofold product, there almost certainly doesn't seem like. What I was curious about is obstructions die out when one performs a symmetrization, which is why I kind of jumped in and I wondered whether you just meant the annulus or you meant the symmetric twofold product.
Well, maybe that would be actually the way to approach it. Yeah, no, yeah. Again, or you could look at products of, say, the annulus and the disc or something like this. I don't. Again.
So in one variable, there are results that when you replace the disk by one of the half planes, say the right half plane, then one studies operators whose spectra are contained in a cone. Such things might very well be possible here. This will be much more difficult, but possible.
Okay. Well, thanks.
If there are no more questions, then let us thank the speaker.